let us draw BMD and SFD for simply supported beam. Very simple cases of simply supported beam. You can say them that these are the standard cases. Let us start with a very simple case. Let us take case 1 of simply supported beam. When the beam is subjected to a point load at the midspan. So W is the point load, and this is the simply supported beam. W is acting at L by 2 from both the ends. So it is acting at the midpoint, and we can label the beam as usual A, B and C. So our first step is to calculate support reactions. So since we do not have any horizontal force applied on the beam, there will not be any horizontal reaction at support A. We will get only two vertical reactions. The vertical reactions are these. We will get VA and VB. So these are the reactions, and we'll plot our bending moment diagram and shear force diagram here. So let us start with the calculation of support reactions, application of equilibrium equation to this beam. So if I apply first equation of equilibrium, which says that all the vertical force is equal to 0, I'll get VA plus VB is equal to W. This is my first equation. Now I have two unknown here, so I cannot find out the value of VA or VB. Only from this equation I need one more equation. So in order to write the second equation, I'll use second equation of equilibrium, and I'll take moment about point A equal to 0. So if I take moment about point A equal to 0, I'll get a clockwise moment due to W. So W into L by 2 taking clockwise moments as positive, minus I'll get anti-clockwise moment due to VB. So VB into L is equal to 0. It gives me VB is equal to W by 2. And of course, the load is symmetrically applied. So VA and VB both will be equal to W by 2. So my calculation of support reactions is done. And since we are doing this using the detailed method, so let us take a section. Let us take a section here and one more here, because the load is changing from a span AC to CB. I can take section 1 here and section 2 here. So let us write down our positive sign conventions. So our positive sign convention, if I cut the section of the beam, are like this. These are my positive sign conventions we have discussed at the last class. So these are my positive sign convention. Today I'll take section 1 which is from the end A at a distance of x. We can mark this distance x. So I'll cut the section. So my VA is W by 2, distance is x, and I can mark my positive internal forces from the sign convention here. Now if I apply equation of equilibrium to this section, I'll get the following results. All the vertical forces equal to 0 will give me W by 2 is upward minus S. So this is equal to 0. I want to find out the value of S. So it give me S is equal to W by 2. That is positive. So for span AC, my shear force is positive and constant, and it is equal to W by 2. Similarly, now let us say this is point X. I can use second equation of equilibrium taking moment about point X is equal to 0. So taking M as positive, M is anti-clockwise, so M, and about point X I'll get clockwise moment due to W by 2. So minus w by 2 into x is equal to 0. So my m is equal to w by 2 into x. Okay, x is 0 at point A. This is my point A. So at A, x is equal to 0. So m will be 0. And at C, x is equal to L by 2 and m will be equal to WL by 4. So let us plot this. Positive, this is positive, and the variation is linear. Variation of bending moment is linear, as it is clear from here that it is varying with the first degree of x. So let me plot the shear force diagram first of all. So shear force diagram will be, let us plot the shear force diagram for section AC. The shear force diagram, this C is positive, W by 2. This is my shear force diagram. And my bending moment diagram will be for portion AC, it is starting from 0 and going up to WL by 4, positive. Now from symmetry, now portion AC and portion CB are the mirror image of each other. So from symmetry I can complete the BMD and it will match here. But here in case of FD we cannot do like this, because our force W by 2 is acting upward and W force, external force, is acting downward. So it will bring down the action of W here at point C, will bring down my shear force diagram vertically downwards, and rest of my shear force diagram will be negative, but its value is equal to W by 2. So the magnitude is W by 2. So this is my shear force diagram and bending moment diagram for a simply supported beam subjected to a point load at the midpoint. Now one more example can also be taken. Let us take another example of simply supported beam when it is subjected to a UDL. So next case is a simply supported beam which is subjected to UDL over the entire span. Let us say the intensity of UDL is W kilonewton per meter and the length of the beam is L. The first step is to find out support reactions. So my support reactions are two, VA and VB. So let us calculate the support reactions using equation of equilibrium. So my VA plus VB is equal to total load. The total load is intensity into the length over which the UDL is acting. So intensity of UDL is W and it is acting over the length L. So this is my first equation, and if I take moment about point A and put that equal to 0 here, so I will get anti-clockwise moment due to VB and clockwise moment due to the load UDL. So VB into L is the moment due to support reaction VB at point A minus WL, which is the total UDL. It will pass through the half of the length of UDL over which it is applied, and that is L by 2. So my VB will be W L by 2 and VA will also be W L by 2. Otherwise also it can be seen from the loading that it is symmetrically applied over the beam, so both the reactions will be equal and equal to half of the loading applied. Now for plotting the shear force diagram and bending moment diagram, let us cut a section. Let us cut a section here 1 1 and take it here B WL by 2, and let us say this distance is x, and my positive sign convention says that the internal forces will be acting upward. So my shear force and bending moment, since I am taking right hand side portion of the section, so this is I am taking section 1 1. Now I am going to apply the equilibrium equation over this section. I'll call this point as x. So taking S, the shear force positive, if I use first equation of equilibrium, S is upward plus the reaction is also upward, WL by 2 minus W into X. This is equal to 0. This is the loading, the UDL. The UDL is acting over a length X. So S will be Wx minus WL by 2. I can take W common, so x minus L by 2. So from this it can be said that it is a linear variation. So let us find out at point B, x will be 0, so shear force will be minus WL by 2, it is negative. And let us take the midpoint. Let us take the midpoint of the beam as point C, which is at L by 2 from end B and end A. So at point C, x is equal to L by 2 and my shear force will be WL by 2 minus L by 2, so it will be 0. So the variation is linear and it is negative. So let us plot the shear force diagram. Here let us see, this is point A, this is point B, and this is point C, the midpoint. So it is linear and negative, negative. And I can say this is WL by 2. I'll plot my BMD here. This is my shear force diagram. So for this section, let us move further. Let us go to point A. So at A, x will be L and S will be W into L minus L by 2. So it will be WL by 2, positive. So that means the variation will be like this. This is point C, the point of zero shear force, and this is positive, and this value will be WL by 2, positive. So the shear force diagram is linear and it has maximum values at the support. The maximum value of shear force at support A is equal to reaction at support A, which is equal to WL by 2. Same is the case with support B. At support B, the shear force is equal to the magnitude of the reaction, which is WL by 2, and the point location of zero shear force, it at the midpoint of the beam. Now for shear force diagram, taking same section 1 1, and taking moment about point X, this is point X. So let me I can redraw this section, or I think we can see here. So I'll take moment about x equal to 0 and I'll try to write the equation here. Let us take m as positive, which is the internal moment. Then it is clockwise and I'm taking the clockwise moments as positive. Then due to the external load, I'll get another clockwise moment. So minus W, x is acting, this UDL is acting over x and it's action will pass through Wx by 2. So this is my moment due to applied UDL. Now it will be plus because both are clockwise. Now minus WL by 2 into x, the moment due to reaction, moment due to applied load, and internal moment. So this is equal to 0. Let us further simplify the equation. Plus Wx square by 2 minus WLx by 2 equal to 0. So I can write m is equal to WLx by 2 minus Wx square by 2. So it is a parabolic variation. So my BMD for this case will be parabolic. Let us find out. We are starting from end B. So at point B, x is equal to 0 and m will be equal to 0. At C, x is equal to L by 2 and m will be equal to, substitute x is equal to L by 2 in this equation which we have just derived. So W into L by 2 divided by 2 minus W L square 2 into 4. So let us take WL square common by 4 common and I'll get 1 minus 1 by 2. So my answer will be WL square by 8. WL square by 8. Let us draw the bending moment diagram. Now bending moment diagram is positive and it is 0 here at point B and it is maximum here and the variation is parabolic like this. And from symmetry I can draw the rest of diagram also and I'll prove that at point A this is 0. So this is positive with maximum intensity at the midpoint which is WL square by 8. This is my BMD. So for a simply supported beam which is subjected to UDL over the entire span, only UDL, no other loading, the bending moment, the maximum bending moment will be at the midspan, at the midpoint of the beam, and the maximum bending moment will be equal to WL square by 8. Now same equation, for the same equation, this equation which is the moment equation, at point A x is equal to L. So substitute x is equal to L in this equation, I will get m is equal to W into L by 2 minus WL square by 2 which is equal to 0 as we have obtained here. So this is bending moment diagram and shear force diagram for a simply supported beam subjected to UDL over the entire span. Thank you so much.